Give me an answer.
Because it just changes one thing to another.
And twice. I'm just going to close this and see what the responses were later. Try to keep you honest. Sometimes I'll grade these like, you got to get it right, but if that's the case, I'll usually tell you, I want you to get this right. Let's see, the first digit was, I hinted that the first digit was a 1, but is that right? No. So even though indeed, if I were to weigh a match, to weigh it on a sensitive scale, and then burn it, this has been a week of Mondays or something. There we go. And then burn it, and let it burn. I can let it burn I can stop it now, or I can continue to let it burn all the way down, and then blow it out at any point and weigh it again. It really does weigh a little bit less. But did we lose some matter? So is the matter destroyed? Oh, so it's false, and what's the second digit?
6.
Conservation of matter. Atoms aren't, in chemical reactions, mass is not gained or lost. The total amount of mass stays the same because we're not destroying or creating atoms. That's not always true in nuclear science, but in chemistry we'll always say that's true. In questions like this, if my iodine in my container and it's all sealed up, iodine's a cool purple crystal. When you warm it just a little bit, it changes into a gas, so it's like a purple haze of sorts. Well, the weight after I heat it up, let's see, I had 1 gram of iodine in the tube, and I closed the tube up, and together they weigh 27 grams. So afterwards, they'll also weigh 27 grams. I mean, sometimes heating screws things up because there's convection currents and it messes with your balance. But for the most part, we're not going to gain any mass, we're not going to lose any mass. For breaking old bonds and forming new bonds, sometimes the fluffiness gets away. Oh, so for example, my next question. Look at this one. Okay, so mass is conserved, so be whatever. Stupid clicker thing. I'll post that, you can look at it if you want it. Nothing? This one's way too complicated, I'm already behind in my lecture. But did you know that, say for example, acid rain, acid snow can eat buildings away and marble statues? It's a common chemical reaction. You can do it in the kitchen. You just take vinegar and baking soda. And so in this type of reaction, I could say, the law of conservation of matter is so fundamental, we don't even bother to prove it. Sometimes laws are so well accepted that, and it's been thought of and studied enough, we're just going to take it for granted. So if I had 500 grams of vinegar, and I had 25 grams of baking soda, and I add 500 plus 25, it's a cool, fun mess. It's actually endothermic, it's pretty weird. Shouldn't I have 500 plus 25? So if I were to weigh that now, it'd be 525? You're right, it's not. Because why? Because we're gonna say we didn't. What about all the bubbles? Did the bubbles weigh something? And did the gas get away? And if I were to weigh it on a scale now, it probably wouldn't weigh 525. It probably would weigh something less than that. And the amount less could be simply arrived at through subtraction. Yeah. So how long has it been since you've seen a chemical equation? The masses should add up. So the left-hand mass and the right-hand mass should equate, and so the mass of gas that bubbled away in this long blah, blah, blah was about 3.2 grams. It's a reasonable amount of gas to lose. Okay, those questions are so involved that I don't know how. We'd have to keep it pretty simple on an exam question, but it could be phrased in a fairly simple way, I think. So here's the cathode ray tube. J.J. Thomson is famous and getting credit, and his team of physicists, I guess, for correctly. Crook was his name. I forget his first name. This is called the Crookes tube. And when I turn it on and up a little bit, oh shoot, I forgot my magnet. I gotta go grab my magnet when you answer are watching this next thing. Remember how the magnet deflected the beam of electrons? And I can't see the beam of electrons, but I can see them hitting this white screen. And when they hit this white screen, the screen glows green. It's got an eerie, scary sound because of the power converter here. That's a high voltage. Got to be careful with it. But that is a beam of electrons. And with the electric fields and magnetic fields, he measured the forces and the deflections and used simple physics, second semester physics, to figure out the charge to mass ratio for those electrons. And he correctly deduced that those electrons were part of atoms. Parts of atoms. Yeah. Parts of atoms, and not only that, so he didn't figure the charge, he didn't figure the mass, he did figure the charge was negatively charged, but he was able to find the charge to mass ratio. Yeah, charge to mass ratio. It took a few more years for some other genius to come up with the reason, to come up with the exact charge on the electron. This is a simple cartoon. I wonder if I can, is that running? Yeah, that's running. Oh, that's boring. Let me grab a magnet. So there's a stream of electrons. We won't study cathodes and anodes this semester. We will in Gen Chem 2, but the cathode spits off the electrons, so they're coming from left to right. And the magnet or an electric plate can deflect the beam of electrons. Can you see that? I don't know if you can see that. Whoa, yeah, one way or the other. And so he actually measured these. When I bring this close, I can actually feel this thing vibrating a little bit. I'm strong, I can hold it, but I can still feel it vibrating. And so this magnet is interacting with that beam of electrons, and that beam of electrons is interacting with this magnet. And when I say interacting, I mean putting forces on, electromagnetic forces. And he was able to figure out that charge to mass ratio. That's one famous experiment you should know. There's another famous experiment you should know. Shortly after that, Rutherford's gold foil experiment. He shot, Ernest Rutherford and his team, shot magic bullets. He didn't know at the time these magic bullets were actually nuclei of atoms, and he was in the process of trying to prove they existed. He shot these bullets at a very thin sheet of gold foil. This question says, and these magic bullets are called alpha particles. They had recently discovered radioactivity, and so this radioactivity was shot. This is like lead here, so they can't get out this way, but they shoot this way, and they encounter the thin gold foil. After the alpha particles leave the gold foil and strike the fluorescent screen, this is a fluorescent screen, and the fluorescent screen glows similar to the way that screen glows. The question here, I think, is briefly describe to your neighbor. Okay. So I'm your neighbor. Who feels brave? Tell me. Oh yeah. Huh. Which position, A, B, C, D, E, or F, was the most surprising to him? So, who said A? Yeah, why did he say A? Good. So if you're shooting this really heavy, dense, I think I have a video. Thank you. If you're shooting this really heavy, dense bullet, the analogy he used was you shoot a cannonball at a piece of paper, and the cannonball bounces back. The cannonball would never bounce back from a piece of paper. But check this out. I wonder if I can turn that on slide scan. So usually they just go right on through. But every now and then one of them ricochets because it comes close to the nucleus, or even bounces almost directly back toward the machine itself. That's a cool animation. They're pretty accurate about what does happen. I wonder if they'll zoom in. I think, come on, zoom in. Sometimes they'll zoom in on the gold foil. Oh, there we go. No, gold is very peculiar because you can hammer, you can roll gold into just a few atoms thick. Well, a few hundred atoms. But anyways, so most of them go right on through because atoms are mostly empty space. Atoms are mostly empty space. Oh, all right. So that was that.